Thank you very much, Colm. Thank you very much for the organizers to invite me. And I'm going to talk about a supergranule aggregation process for constant heat flux-driven convection. And that is a joint work with Philip Fievig, who did all the simulations and most of the data analysis, and Janet Scheel from Occidental College in Los Angeles. Oops. What's the, oops, let me see something.
If you click the screen, I think you can advance it.
Okay. So let me motivate my talk with solar convection, which takes place in the outer shell of the sun. And as you can see here, convection is there organized in a hierarchy of structures. These are the granules, the building block of the convection at the surface. They have a diameter of about 1,000 kilometers. They live for about 10 minutes, and the velocity is about 3 kilometers per second, and they can be observed optically. Next, it's followed by supergranules, which are observed by either helioseismology or by granule tracking. And the picture which you see in the top is a surface divergence, which indicates the up and down welling regions with respect to these supergranules. So they are on a much bigger scale, 30 times bigger than the granules. They live for about a day, and the velocity is a little bit smaller with 500 meters per second, the characteristic velocity. And that is followed in the hierarchy by the giant cells, which are supposed to be stretched out over the whole convection zone with a depth of about 200,000 kilometers. Very long-living objects, about 1 month, and a very small velocity, characteristic velocity with 10 meters per second. And the existence of these giant cells is still under question and is still a matter of ongoing research. That's why I've put a question mark there. So, but granules and supergranules are definitely existing. And the question is, the point is that in the simulations, in global simulations of solar convection, the supergranules can still not fully consistently reproduced in these simulations. And that means there's still a lack of understanding of the structure formation process. And our motivation is to go to a much simpler system and to see what's going to happen there if we are varying the boundary conditions. And that will be the Rayleigh-Bénard convection flow. You see the model which we are simulating in direct numerical simulations here on this slide. We have the Boussinesq equations, the mass, momentum, and the energy balance. The domain which we are simulating has a square cross-section with 60 times the height of the cell, so very extended domain. For simplicity, we are choosing a Prandtl number of 1. We are aware of the fact that the Prandtl number in the solar convection case, for instance, is about 6 orders of magnitude lower than 1. And the Rayleigh numbers are defined in correspondence with the boundary conditions that we are choosing for the temperature field. We actually choose 4 different sets of boundary conditions which follow from combinations of the velocity and temperature boundary conditions. These are the no-slip conditions for the velocity field at the top and at the bottom plate, or the free slip condition at the top and bottom plate. And they are combined with the temperature conditions. These are either the Dirichlet conditions, where we prescribe constant temperatures at the top or bottom, or we prescribe constant fluxes, which are given here by the normal derivative of the temperature field. And the side planes are periodic in all cases. And we have to keep in mind that the Rayleigh numbers of the Neumann case and the Dirichlet case are connected with each other when you want to compare these simulations. See, for instance, the reference which I have given here. The system reacts with the turbulent heat and momentum transfer, and the corresponding measures are the Nusselt numbers, which are defined here for the Dirichlet and Neumann case, and the Reynolds number at the bottom for the momentum transfer. So let's dive into the simulations. And what you see here is a horizontal cross-section through the temperature field for a snapshot of the simulation. And we are comparing the 4 different sets of boundary conditions: Dirichlet no slip, Dirichlet free slip, Neumann no slip, Neumann free slip. And the planes are always taken below the surface inside the thermal boundary layer. And the Rayleigh numbers are 10 to 4, 10 to 5, 10 to 6. These are given for the reference case, which is always DNS, the one in the right column. You observe for the Dirichlet case the characteristic patterns of the temperature field, which are well known and which continue to exist also into the fully turbulent regime, as you can see in the bottom to the right. The situation changes completely if we go to the flux boundary conditions, where you see basically a big pair of convection cells, red and blue, which fill the whole domain. And that is something which we observe for all 3 sets of Rayleigh numbers. So it looks like that the temperature boundary conditions really matter for the structure formation, much more than the free slip or no slip condition for the velocity field, simply because the temperature field in these corresponding cases look very similar, as you can see. Okay, so let's recall what is known for this particular case of Neumann boundary conditions from the theory. So we have to go back to old works by Sparrow and colleagues, and I'm showing you here results from Hurl and colleagues from 1967. And what they have actually considered is the so-called conjugate heat transfer problem, where you really have a finite plate, which has a finite diffusivity or conductivity. And then you go to the limits that you have an ideally conducting plate, which is the limit of kappa fluid to kappa solid is equal to 0. And when you are conducting a stability analysis for that case, you certainly recognize the classical result of a critical Rayleigh number of 1708 and a critical wave number A of 3.11. If you go to a perfectly thermally insulating plate, it's exactly the Neumann case, and then this ratio turns to infinity. And there, the critical Rayleigh number for no slip boundary conditions is 720. In the free slip case, it's 120. Sorry. The critical wave number then is 0. That means in an infinitely extended layer, the convection cell will stretch out as much as it can, and the wavelengths will tend to infinity. We have a finite domain, so there is a minimum wave number that we can obtain in our setting. And what I show you here is the aggregation process that leads to this big cell, which we also term a supergranule. We start with a thermal equilibrium. That means we take the equilibrium profile, put a little bit of noise onto the profile, and then we let the system evolve. And then it starts to develop coarser and coarser patterns. And as you can see, if you look at the time, which is measured in convective time units, it takes a very long time until you reach into this kind of saturated state. In the middle row, you see the corresponding Fourier spectra, which we have taken in the planes where the pictures in the top row are shown for. And also there you see that the Fourier modes accumulate magnitude in exactly the 4 minimum wave vectors which are obtainable in this particular setting. When you then start to average with respect to the polar angle phi, you obtain spectra, and these spectra show a typical behavior as you would see it in an inverse cascade process. They are piling up at the smallest possible wave number, and that happens for all quantities like temperature variance, like vertical velocity, or the co-spectrum between both, which measures the convective heat flux. You can do this close to the surface, you can do it in the middle, so that's a pretty robust feature. And this process is observed for all Rayleigh numbers that we actually could obtain in the series where we have free slip boundary conditions for velocity and Neumann for the temperature. So this is again the temperature field. We could go up to almost 10 to 8. And this is the corresponding streamline plot of the surface flow in these cases. And what we observe here is that the larger the Rayleigh number, the longer you have to wait. For the biggest Rayleigh number, almost 20,000 free fall times. So that's a pretty long simulation you have to run in order to get there. Okay, you can also analyze the turbulent heat transfer. So what we have done is we have applied a filter in the Fourier space, and then we are looking at the transport due to this large and growing structure and to the remaining part. And you see that the share of this big structure is steadily increasing here at the cost of the remaining part, but the global Nusselt number remains more or less unchanged in time. So the time average does not vary over these long simulations. Okay, so now we are going a little bit further. And again, we look back into the theory, and there's a work by Chapman and Proctor where they basically extended these considerations by Hurl and colleagues, considered 2D convection in a finite box. So in a finite box, you have a minimum wave number, which is prescribed by the horizontal lengths. What you see to the left here is the stability boundary, and the point of the simulations or of the considerations of Hurl is exactly here on the y-axis. And what they have basically done is they have basically done an expansion of the critical Rayleigh number as it is given here. You have a parameter epsilon, a small parameter epsilon, and then you can rescale the horizontal scale and the times and the corresponding derivatives as it is shown here. You plug this into the Boussinesq equations, and then you do an addition and expansion of the temperature and of the stream function in your flow. And that in this way, you get a hierarchy of equations. You get solvability conditions, which result in another equation. You look for steady solutions and their stability. So I won't go into these details here, but I would like to point to a sentence which the authors have written down in the abstract of their paper, which says, stability analysis reveals, however, that each mode is unstable to one of longer wavelengths than itself, so that any long box will eventually contain a single roll. And that's exactly what we have observed, as you remember. Okay. So let me take a little breath and a little pause and summarize what we have seen so far. We have seen that the constant flux boundary conditions lead to the formation of such a supergranule in an extended domain. At least for the case of Prandtl 1, we have seen that. It's more or less independent of the velocity boundary conditions, and we have observed it for all accessible Rayleigh numbers. That means also in the fully turbulent case. The larger the Rayleigh number, the longer this aggregation time was. And we know from theory that at the onset, the critical wave number is 0 for this case in an infinitely extended layer. And we also know from a finite domain analysis and the weakly nonlinear theory that these convection rolls grow up to a wavelength of L, which is the horizontal extension. So it looks like that the convection flow does not forget where it comes from, even though we are fully turbulent and far beyond the critical Rayleigh number. So can this be quantified in the turbulent case? And we decided to conduct a Lyapunov analysis to look into this. And let us recall what this implies. Well, we consider our convection flow as a dynamical system, and the evolution of this flow is a trajectory, which I marked here in red, through a very high dimensional phase space. And what we are now doing is we are putting a little perturbation on this trajectory and have a neighboring trajectory, and then we are quantifying the exponential separation from the original one. And this is typically done in this rescaling formalism, as I have tried to indicate it here in our picture. We have a lot of degrees of freedom in our system. So that the number of degrees of freedom can be estimated when you basically consider the 3 velocity components and the temperature field at each grid point. And the number of grid points is roughly the number of spectral elements times the collocation points in each spectral element to the power of 3, which is determined by the polynomial order in which you are expanding all your fields. So this is for the largest case, something like more than 10 to 10. So it's clear that we are not able to do any analysis in terms of getting all Lyapunov exponents and the corresponding Lyapunov vectors. So we are focusing to the leading one, the leading exponent, which is defined by this relation, and the corresponding leading Lyapunov vector, which has a norm that is given in this case. So we are basically solving one set of equations for the evolution of the perturbation together with the flow. Okay. So here are the linearized Boussinesq equations. And so we are solving the full nonlinear equations, Boussinesq equations, together with this set of linearized equations for our systems at hand. So we are not the only one or the first ones who have been doing this. I would like to point to groups who have done this already in the past, in the weakly nonlinear regime of convection right above the onset of convection. And they also even went to analyze a larger fraction of the Lyapunov spectrum. That means they solved more equations simultaneously with the original nonlinear equations. We have tested our algorithm here for a very low Rayleigh number of 5,000 Dirichlet and no slip, where we find the Rayleigh-Bénard convection flow in the spiral defect chaos regime, as you can see here with the temperature field in the midplane. And you see indeed that there is a kind of defect formation here in this short sequence. And this is in line with a high amplitude event of the temperature component of the Lyapunov vector. So the Lyapunov vector consists again of 4 components, and we are focusing here to the temperature component of this Lyapunov vector. So that's how it looks for our turbulent case. And we are taking one Dirichlet case and the corresponding Neumann case here. And this is again the temperature field in the top rows of these 2 figures and the corresponding Lyapunov vector component. And whenever there's a change in the pattern, then this Lyapunov vector field gets here a high amplitude region, which is given in yellow. in the Neumann case, you have here these ridges, which are very high amplitude regions. Okay. So now we have done this analysis plane by plane. And we picked those planes where the magnitude of this Lyapunov vector component is largest. This is in the no-slip case somewhere close to the wall, and this is basically in the constant flux case inside the thermal boundary layer. So we have taken the rest of the analysis in the planes which I indicated here by these two arrows in my slide. So here you see again to the left the Lyapunov exponent in green, the corresponding Nusselt number in this flow. They are fluctuating as you can see here. And then we are taking spectra of the temperature and of the component of the leading Lyapunov vector. These are the red spectra, and we are looking at the first maximum, local maximum in the spectrum, the first peak when we are coming from the left. And we see that in the Dirichlet case, this maximum stays constant with respect to time, while this first maximum starts to grow as long as the box size is reached. This is the second maximum, which is, for instance, here in this particular example. So we basically see by this Lyapunov analysis exactly the same what Chapman and Proctor found in their theoretical analysis. So the next step is, and I'm just giving a little brief outlook before I conclude, that we are also trying to extend the Rayleigh-Bénard setup and trying to move forward towards solar convection to the solar convection case. And the first step is to introduce a temperature-dependent diffusivity in your Boussinesq model, which makes it immediately non-Boussinesq, as you can see here by the mean temperature profile, which is given in red. And we have a rather strong variation of the diffusivity, which is typical for stellar convection, where you always have a huge stratification in your convection zone. So at least for the diffusivity, we are reproducing this fact. And we have a diffusivity that is 500 times larger at the bottom compared to the top. So we have basically a Rayleigh-Bénard setup, which is at the bottom low Prandtl and at the top high Prandtl. And the corresponding reference cases are given here with the green and the blue mean temperature profile. And here you see how that convection is organized. This is the low Prandtl bottom reference case, the high Prandtl top reference case, and this is the mixture of both, where we basically observe what is typical in these stellar convection cases. We have a coarse convection pattern, which is prescribed by the low Prandtl structure, and we have these small scale granules on top of these bigger convection features. Okay. So the plan is to basically combine this kind of analysis with what I have been mentioned before. And that brings me to the summary and the outlook. We have observed a supergranule aggregation in an extended Rayleigh-Bénard convection flow with constant flux boundary conditions, independent of velocity boundary conditions. And we have conducted a Lyapunov vector analysis that demonstrates that the system tries to develop larger and larger structures as long as it is possible. This process is very gradual and slow, as we have seen. And now the question is, what brings it to a stop in a real system? And our expectation is that an additional physical process is required. For instance, slow rotation, which is actually the case in the solar system. And I just refer to a recently published archive preprint by Vasile, Julian, and Featherstone on that. All the details on my talk can be found in this archive preprint. I would like to thank our funding agency, the German Research Foundation, and the Supercomputer Centers for funding computer time, and I thank you for your attention.